is the climate changing? Should we be going on a CO2 diet? And I want you to think about that for a time, and maybe we can come back to that towards the end of the session. If we're going to talk about climate, is to understand the where climate exists, and it exists in the atmosphere. And if we look at this particular slide, you can see the atmosphere goes up from the Earth's surface up to a total of around 500 to 800 kilometers. And if you look at the first 15 there, you can see that white band on just above the surface of the Earth. That's really the important part of the atmosphere that we're interested in. That's where all the weather and the climate actually happens. There's a number of features, of course, with the climate that we need to understand, and that is that there's these layers. We talk about the stratosphere, the troposphere, and this picture from NASA, which is really a sort of a startling picture, I feel, even shows you a thunderstorm there. But down in the lower left of the screen, you can see that the atmosphere is made up of a number of gases. And if we have a look at that, and I don't know if you can see me in this room, but imagine that I'm in this room, obviously, and I'm walking away from the wall to about a distance of 4/5 or about 80%. Can anyone tell me what gases I'd expect to find on that side? But anyway, let me answer the question. Those gases, of course, would be nitrogen, and if I then, from where I'm standing right now, walk over to the far wall and the remaining roughly 20%, those gases would be, and the answer, of course, would be oxygen. If we look at the number of gases in just a few millimeters along the wall, what gases would they be? And those would be essentially everything else. So our atmosphere is made up of mostly nitrogen, and then about 20% or so oxygen, and the rest is everything else, which is namely water vapor, as well as the greenhouse gases and inert gases that perhaps you've been studying in your science or in chemistry in particular. It's those greenhouse gases that make up very much less than 1%, as you can see on that slide with the atmosphere down in the lower part there. The greenhouse gases are responsible for the climate that we experience today. If we were to take those greenhouse gases out of the atmosphere, anyone know what the temperature of the Earth would be? Anyway, the temperature of the Earth would be around -18 degrees. So if we take those few greenhouse gases away, the temperature would be considerably colder than what we're used to, and what we'd find is that, of course, it would be uninhabitable. With the greenhouse gases, and again making up very much less than 1%, the temperature is much more habitable at an average temperature of about 15 degrees. The climate system is really made up of five interacting systems, and if you have a look at these, some of them you're going to know, and some you might not. Right at the top, of course, you've got the atmosphere, and then if we go around clockwise, anyone tell me what the cryosphere is? Anybody heard of the cryosphere? But the cryosphere is essentially the ice caps, glaciers, snow. It's any of the water that is frozen. And if you look at some books, what they do is they'll put the cryosphere and lump it in with the next one, which is the hydrosphere, which of course you're probably more familiar with. Next, the lithosphere is the Earth's crust. And then finally, the biosphere is what you study in biology, which is that layer on Earth where life is found, and the interactions are significant. And what a teacher might ask you, for example, is to tell me what are the processes that are going on between those arrows. So if you have a look at the arrows between the atmosphere and the biosphere, can anyone tell me what a process might be that would be going on between the atmosphere and the biosphere? One answer might be photosynthesis, that green plants absorb carbon dioxide from the atmosphere and give off oxygen, and animals through respiration, and also green plants do the same thing. That is, through respiration they take in oxygen and give off carbon dioxide. So cellular respiration as well as photosynthesis would be two interactions. Another one might be, what about an interaction between the atmosphere and the hydrosphere? And of course, one of the largest cycles that we've got is the hydrologic cycle, and that'll be an interaction there. So we get the process of evaporation of water from the oceans, and as well as from streams and lakes, as well as then precipitation of either snow or rain or sleet, hail, etc., coming down. And so that'll be another interaction. Okay, there's a number of systems that interact with the climate system, and the five that I've mentioned in the center of the graph are really ones that are internal factors for the climate system. The things that impact it are most important, and that is solar energy and the Earth's orbit, as well as plate tectonics. And these factors are outside the climate system, and what that means is that the factors that are outside cannot be impacted by climate. In other words, climate can influence the atmosphere very definitely. It can influence the Earth's crust very definitely. What it can't do is it can't influence the solar energy, or it can influence the Earth's orbit, and it can't influence plate tectonics. Also, all those factors on the left-hand side of the screen are outside the system. Now, the things that are affected by climate, of course, are the composition of the atmosphere, as well as sea and ice and vegetation and the oceans and so on. And that's one of the more important aspects as to what the climate does interact with. If I ask you what it's going to be like tomorrow, you're probably going to give me two answers. You're probably going to tell me how warm it's going to be or not, and what it's going to be doing by way of precipitation, if there's any. And generally those two factors are central to what we describe when we ask, well, what's the weather going to be like? And we might ask what the humidity is going to be like, or what the ozone index might be, and a number of other factors. But for the most part, we're interested in temperature and we're interested in precipitation. That's weather. Climate is the weather that occurs over a period of 30 years. And you really can't talk about climate until you're in a time span of at least 30 years. And so in Burnaby, for example, or Vancouver, or pretty well anywhere on the West Coast, if you describe what your climate is, can you tell me what that would be? Yeah. What would in Burnaby, for the most part, you'd say you have a middle latitude climate that is for the most part wet, or a wet area, versus we in Calgary, if I were to describe our climate, I would say we're in a dry area. And so often precipitation and evaporation are two important factors that you describe when it comes to climate. So what you're looking at now, if I can do this, is you should be looking at this slide here. Now this is a difficult slide in the sense that it looks really complex, and when I talk to students I say, okay, well listen, there's a number of things to do right at the outset, and the first thing you should do is have a look at the title, and of course what we're talking here is greenhouse gases and temperature, and then start to examine the coordinates. And the coordinates on the bottom is time, beginning over on the right hand with 0, and then going back to 420,000 years before the present. And if you have a look at this particular graph, what you see then is that the temperature, as well as the two gases, carbon dioxide and methane, which are shown on the left-hand vertical axis, have changed significantly over the last 420,000 years. My point of this graph is the following. Temperatures changed in the past very significantly. And if we look at the right-hand vertical axis once again, and you see where the 0 is, that 0 actually refers to what the ambient temperature of the Earth's surface is right now. In other words, it's about 14.4 to 15 degrees Celsius. So if we take the average temperature at every point over the Earth's surface, the air temperature at ground level, we'd find it to be somewhere between 14 and 15 degrees Celsius. If we have a look and go back in that graph to about 25,000 years ago, if we go back in the graph to about 15 to 25,000 years ago, you can see that we were in an ice age. And in fact, where you are sitting and where I am, on top of us would be about a kilometer or two of ice. And there was a huge ice sheet covering a good part of North America. But if you go back about 125,000 years, you can see we're in a warm period again. And then before that, we're into another ice age, and then a warm period and an ice age. And we can see that these have cycled about every 100,000 years or so. And so if we progress into the future, perhaps another 10,000 years, we might be looking at having another ice age occur. This is important because what it shows is that temperatures changed in the past long before humans were on the scene. Not on the scene. There were humans 420,000 years ago, don't get me wrong, but there weren't humans that were doing anything to the atmosphere like we are today. What I've done is I've shrunk this graph and extended the vertical axes. Here you're looking at where carbon dioxide is today at 385 parts per million. And you can see that it's much higher than what it's been in the last 420,000 years. Now that's significant, I think. If we click on the next one, you should see 560 parts per million show up on the vertical axis again. And that's where methane is projected to, or beg your pardon, that's where carbon dioxide is projected to be by the end of this century. If you do one more click, you'll see right at the very top of the graph, right above the title gases, you should see that we've got 1,780 parts per billion of methane. And that's where methane is today. Not where it's projected to be, that's where it is today. So my point is that if we say, yes, temperatures changed in the past, and so has the level of carbon dioxide and methane, but today it's never been as high as it's been any time in the last 400,000 years. And so regardless of what we might feel regarding climate change and whether or not humans are having anything to do with it, the level of the gases, both carbon dioxide and methane, which are important greenhouse gases, that should be getting our attention. You can see there on this pie graph that water vapor is the most important of the greenhouse gases, and yet nobody's talking about water vapor. What they're talking about is they're talking about carbon dioxide and sometimes methane and sometimes nitrous oxide and so on. Now the reason they don't talk about water vapor is because the amount of water vapor in the atmosphere is not changing. Now if you accept that, one could argue and say, well, wait a minute. If our temperature is getting warmer, in other words, I don't know if you noticed in Burnaby that the temperatures gotten warmer in the last 5 to 10 years perhaps, but if we have a warmer air temperature, then doesn't it follow that that warmer air can hold more water? And the answer is, of course, it would. And if water vapor is a significant greenhouse gas and we've got more water vapor in the atmosphere, then isn't that going to contribute to more warming? And the answer is it would. And so don't you then invoke sort of a positive feedback or a vicious cycle, if we like, whereby a warmer atmosphere holds more water vapor, and that water vapor then is a greenhouse gas which will cause more warming, and we get a positive feedback cycle. The answer is yes, it would, very definitely. But one should also ask, well, what's going to happen to water vapor once it gets in the atmosphere? And the answer is, well, what's happening in Burnaby today? And what you've told me is that you've got some cloud cover, and those clouds are releasing water vapor, and it's coming down as precipitation. And so the answer is that some of that water vapor is going to form cloud. And tell me what happens to the temperature when you've got cloud cover. And obviously the clouds reflect solar radiation, and that's going to reduce the amount of heating. So the water vapor feedback could be both positive, as we described just a moment ago, or it could be negative, because some of that water vapor forming cloud is going to reflect sunlight. And so the whole water vapor feedback system is really a difficult one that scientists have to try and grapple with. Taking water vapor out of the equation, so to speak, you then find that carbon dioxide is the most significant of the greenhouse gases, and then methane, and then all the others, which is nitrous oxide. The CFCs are chlorofluorocarbons, and those chlorofluorocarbons are what used to be in refrigerators and air conditioners in automobiles, which have now been replaced by another chemical called hydrofluorocarbons. And the last one is ground level ozone. And generally those gases without water vapor in the equation are the main contributors to what we to the enhanced greenhouse effect. In other words, the greenhouse effect that humans are having an impact on. Okay, the next slide, the hydrologic cycle. I just want to show you this is the largest cycle in terms of movement of matter that occurs on Earth. And I don't know if you can imagine looking out your schoolroom window there, and if you can see into the distance 1 kilometer. And then imagine that you turn at right angles and you look another kilometer. So there you've got an area of 1 square kilometer. And then imagine looking upward 1,000 meters. In other words, another kilometer. Well, fill that space, that volume, with water. And that's what we have multiplied by 536,000 cubic kilometers. So that's the amount of water that cycles on Earth every year. So the water vapor is actually a huge factor in terms of greenhouse gases and in terms of what kind of climate we have on in various parts of the planet. Okay, now if we go to the next slide, this one describes for you some of the features of the greenhouse effect, and let me take you through it as quickly as I can. If we look at solar radiation coming into the atmosphere, about 31 or 32% of that gets reflected. And so if you look on the left-hand side of that slide or on your handout, you can see that clouds reflect about 22 units of the 100, and from the Earth's surface you get about 9 reflected. Can anyone tell me what the term is that you use for the reflection of heat energy or light from Earth's surface? Anyone? Albedo, right? Anyone knows that if it's really a hot sunny day out, the type of clothing you might be wearing would be what? Light or dark? Outside, you're probably going to wear light clothing. If it's a cool day and you want to maximize the amount of energy that gets absorbed by your clothing, you'd wear something dark. And basically we're saying the same thing on Earth's surface. If we have an Earth's surface or a field that's covered with snow, as we had in Calgary a few days ago, most of it's melted now, but if you have a field covered with snow, the albedo is going to be much higher because the light will be reflected, and that will cause cooling. Clouds, of course, reflect it. Anyway, so you get a total of about 32 units reflected. About 20% gets absorbed by the atmosphere itself. And then the remaining 49, or roughly half, gets absorbed by the Earth's surface. When energy strikes the Earth's surface, in this case solar radiation, which is in this case mostly visible light, when it strikes the Earth's surface, it loses some of its energy, and it gets degraded into heat. And you've maybe studied this as the second law of thermodynamics, that anytime you do an energy change from one form to another, you're going to lose some of that energy in the form of heat. And the same is true with sunlight, visible light striking the Earth's surface. It gets absorbed and it causes warming. And that warming is re-radiated from Earth's surface as infrared radiation. And that infrared radiation is then trapped or absorbed by greenhouse gases in the atmosphere, that very small percentage that I talked about at the beginning, and that infrared radiation is radiated back to Earth's surface. It's radiated in all directions, but in particular back to the Earth's surface. And that contributes to about a 33 degree Celsius warming of Earth's surface. if we take out the greenhouse gases out of the atmosphere, the Earth's temperature would be minus 18 degrees Celsius. But with those gases present, the Earth's temperature is about 15, and the difference between a minus 18 and a plus 15 is about 33 degrees Celsius. Ultimately, after the warming, all those gases, or I beg your pardon, all that heat escapes from Earth, and so you get a balance of 69 going out, or 68, plus 31 going out from reflection, plus 69 leaving also. What this does is show you carbon dioxide concentration in the atmosphere in Mona Loa, Hawaii. And even though it's taken at the top of an active volcano, you'll notice that the line is a zigzag line. And that zigzag line is due to seasonal fluctuations. In other words, we talked a moment ago about photosynthesis and respiration. And when the zigzag line goes down, that means that plants are absorbing carbon dioxide from the atmosphere, causing it to drop slightly. And then during the winter, you get the carbon dioxide being released through the process of respiration and the absence of photosynthesis. Now, this is a difficult concept, and what's difficult is that when you start talking about seasonal variation, we're entering a period of late fall and soon to be winter in the northern hemisphere, whereas in the south they're into their spring and soon to be summer. And so when you talk about seasonal variation, one's got to pay attention to which hemisphere you're in. And in this case, the northern hemisphere, because you've got most of the land mass in the Earth in the north, the northern hemisphere has a greater influence over the cycling of these seasonal fluctuations of carbon dioxide than would the southern hemisphere. If you look at the graph, you can see that it's increased significantly. And about 60% of that increase from 1960 to 2005 is due to human burning of fossil fuels, as well as deforestation, as well as other processes, industrial processes, and particularly agriculture. Nitrous oxide, and again, you can see that there's been an increase, and most of that increase has taken place this century. Methane emissions, and again you can see that the increase has gone up again in the most of it in the last century, and particularly in the last half of this century. And that slide also shows you some of the sources of methane. The next slide shows you the temperature on Earth over the last roughly 140 years. And you can see that if we look at the 14 degrees, which is taken as an average temperature based on the period of 1961 to 1990, that during that period the temperature was about 14 degrees, and so that's what that 14 degrees comes from. But you can see in the last roughly 20 years that the temperature has gone up significantly on a global basis. So the answer probably is due to an increase in solar activity, solar energy output during that year. And then the response in Earth was that there's been about a 4-year period of extreme El Nino, which is a movement of heat in the oceans in the tropical areas from Southeast Asia across the Pacific to Ecuador and Peru in South America, and that movement has also contributed to an increase in temperature. But probably in the most part you have to go back to solar activity. And so the short answer would be that there was an increase in solar energy output from the sun during that year or immediately prior to that year. That's good. What I do, if you're still on that slide of the global mean temperature changes, if you're still on that slide,
yes.
as I said at the outset, really you can't talk about climate unless you're talking about a period of at least 30 years. I'm not quite as old as dirt, but getting there. I've been retired from teaching now for 8 going on 9 years. But anyway, if you trace yourself back in that and try and find the year 1953, 1954, and have a look at the blue line on the graph there. Can you see that? If you have a look at that blue line extends well below the 14-degree axis. That's the horizontal axis going across the middle of the graph. That blue line, I came to Calgary from England as a young boy in junior high school, and the first thing my mother did was get me a job delivering papers, and it was during that line, that blue line that goes down in about 1953, 54, 55, that I was delivering papers, and I can remember freezing my butt a number of times. It was bitterly cold. Now, students in grade 10 and high school that only have anywhere from 15 to 18 years of experience, and maybe of that is maybe 10 or 12 years of memory about what the weather was like. It's really difficult to say, well, okay, can you remember when, you know, it was different from what it's been in the last 5 or 10 years? And the answer is you can't. You might remember 1998, 1997 that was particularly warm, but probably not that much, because it wasn't that much warmer in the last 2 years, because the last 2 years have been the second most warmest on record. And so it's only through the benefit of my age and that sort of what I can remember as to what the temperature was like, that during the 50s, actually from the 40s to the 70s, there was concern globally that the Earth is going into another ice age, and that's indicated on that graph by those blue lines. You can see where we are by way of the changes in tundra, forest, and grassland boundaries. In other words, if we look at a doubling of carbon dioxide to from what it is at the present, well, a bit less than that, what it was prior to the Industrial Revolution, up to 560 parts per million, you can see there's a significant change in the boreal forest. There's a significant change in the eastern, the blue area, which is the middle latitude temperate region. But you can also see down in southern Alberta and southern Saskatchewan that there's the beginning of the yellow area, which is sort of semi-arid. And we're seeing indicators of that right now, in the sense that Alberta's talking about drought conditions in the last few years, and although it hasn't been as bad this past year, but there's been significant reduction in water, and they're seeing that in the depth and the extent of the glaciers. I don't know if any of you from Burnaby have been to the Jasper Highway and been to Columbia Glacier, which is sort of a Columbia ice fields, and you can get out of your car and walk right up to the ice field. In fact, you can take one of these track vehicles out onto the glacier. I don't know if any of you had a chance to see that, but what's interesting is when you walk up to the glacier, you can actually see where the glacier was as early as the late 1800s, and there's been tremendous amount of recession in the glacier, and so that's a big concern in the Rockies with the loss of the glacier water through melting. What are the issues? And this is sort of getting to the point of my talk here. Number one, greenhouse gases are higher today than they've been in the last 420,000 years, and most of that increase, about 60% of it, has occurred in the last 50 years, and it's also expected to continue to go up. That fourth bullet there, if you have a look at that on the screen, that fourth bullet, H GHG is human greenhouse gases, and the sources of them, of course, are from fossil fuels and deforestation and so on. And the concern is that what we're adding to the atmosphere is in fact increasing the natural greenhouse effect. The next slide, if you would, talks about the solutions, and there's really only two solutions. Adaptation, and that is we get used to it. In other words, we start saying, well, what can we do to deal with this? A rising sea level, for example, in the Netherlands, in Holland, they've built dikes around it because the area of Holland is actually below sea level. And so for Holland to remain a viable country, they've got to keep the sea from flooding the land. And so building dikes is an example of an adaptation. Abatement or mitigation is the other solution, and that is that we should be reducing our use of fossil fuels. And that has to do with what we're doing by way of our energy use. What are some of the possible impacts for Canada? And you've heard about frequency and intensity of extreme weather events, and if you click it again, health of society is another one, that is heat stress and the risk of heat-related problems. And then the last thing, of course, is what's going to happen to ecosystems and forests. Forest fires in the Okanagan, for example, in the last year or so are indicative of this, and even Vancouver's had, I know, water shortages, and Victoria the same thing in the last few years, and even a place like Tofino on Vancouver Island, some of you may have heard had water rationing at one point. In Canada, what you can expect to see is if you get warming, you're going to get more evaporation of soil moisture. That soil moisture means that you're going to have more likelihood of drought conditions. If you look at the changes to glaciers, the big concern for us in Calgary and southern Alberta is that 90% of our water use is used for agricultural purposes and irrigation, and what this does is place a tremendous demand on the water. And when they look at the snow cover in the mountains, which is the source of our water, that's a real concern. What you're likely also to find is that you're going to get increased weather events, that is more extreme weather events, and people have talked about hurricanes and tornadoes and that sort of thing, and the hurricanes thing is a bit difficult because it hasn't been a significant increase, but certainly drought conditions and lack of water is one of the more important ones. When you get into the whole aspect of urban air quality, if we're saying that the part of the problem is that we've been increasing our use of fossil fuels and through automobile use and an increase in population, then what you're going to get is the likelihood of greater respiratory illnesses in young children particularly, and perhaps the elderly, because of poor urban air quality. There has been some suggestion that as you get a warmer climate, you're probably going to get an increase in unwanted insect pests and possibly diseases moving into an area that weren't obviously accustomed. An example, Inuit in the northern in northern Canada are talking about robins being sighted. Question is, what are robins doing up in the extreme north in the Arctic? They don't normally go up there. They're talking about catching salmon in the Beaufort Sea. What are salmon doing up there? So clearly there are some at least anecdotal indicators of changes that are occurring due to the increase in the temperatures in the last few years. The big question, if you take us right down to the last part of that, the very last bullet on the sheet there is the big question. There are people in society and certainly scientists that will say, listen, there's no indication that we have to be worried about what humans are doing to the atmosphere and to climate. And yet there's others that will say, no, absolutely, the greenhouse gases that are increasing are significant and we should be looking at doing something about it. And for the most part, that's saying, listen, how are we using energy and can we use it more efficiently so that we're not producing as many greenhouse gases as we are? What my take on this is the following. Frankly, I don't know what the balance is, and I don't know that anybody will tell you. What's the balance between the natural greenhouse effect versus the human-induced greenhouse effect because of the greenhouse gases that we're releasing to the atmosphere? I know one thing for sure, and that is that the level of greenhouse gases has gone up significantly during the last 50, 60 years, and that's due to human activities. So the answer is, even though we may be uncertain as to what the real cause of what we're seeing, what seems to be a warming trend, we're uncertain as to what the cause may be, prudence would dictate, in other words, being as safe as possible would dictate that we should be trying to reduce our greenhouse gases as much as possible. And that means addressing aspects of our energy use. This is really a difficult one, particularly for students. If you look at that slide, what you can see in the pie graph is that of the greenhouse gases and the energy we use, about 72% of them are common. That is, you're all in that room and sharing the benefit of the heat and the light and the energy that's used to go to produce those conditions, as well as the building itself, as am I here in Calgary. 28% of our greenhouse gas emissions are due to our individual use. And if we expand that to the lower pie graph that you see on the sheet here, you can see that 50% is due to our transportation choices. In other words, what are we doing for transportation? Now, let me at the outset try to set let me be clear. And what I mean by this is that of all the greenhouse gases that humans produce, your age group, that is from birth until age 25, account for less than 10%. 7 or 8% have been suggested. So you're not the problem. That's important to understand that, and I'd be the first to say that. The problem is me. The problem is the adults and what they're using by way of their lifestyle choices in terms of energy use. Nevertheless, you're going to be in a position someday in the next probably 10 or so years to make some of these choices yourself. And the choice might be, what kind of car am I going to buy? Is it important that it be energy efficient? Let me tell you a quick story, and I'm sensitive of the time, and I want to give you a chance to ask me some questions. I was at a Starbucks at a Chapters outlet having coffee with friends, and there was a fellow and his wife sitting across the table from us, and they were going through an automotive magazine, and after listening to the moo and ah about this car and that SUV and so on, I couldn't help it, and I said to him, I said, tell me, I said, it looks like a new vehicle purchase is in the offing for your family in the near future. And I just wondered, on a scale of 1 to 10, 1 being most important, 10 being least important, where would vehicle efficiency fit? Of all the criteria you've got to use to select a car, what would you use where would vehicle efficiency fit? I thought the guy was going to come across the table at me. He said, vehicle efficiency? He says it wouldn't even get on my list. I wouldn't even consider that. And then he proceeded to tell me how he worked in the oil patch up in northern Alberta, and you know, he couldn't give a care about that aspect. Now, as much as I like to tell that story, I turn it around on ourselves, and I would say to you or to me, when I'm going to buy a car, what kind of car am I going to buy? And how will fuel efficiency be an important criteria in my choice of vehicle? What can you do? Well, what you can do is perhaps influence your parents and suggest to mom and dad and say, listen, I'm going to buy this programmable thermostat, and what I'd like to do before we install it, I want to get all our utility bills for the last year. And you're going to measure what the natural gas consumption is, assuming you're using natural gas to heat your homes, what the natural gas consumption is for the past year. And then you install this, and this is really a simple process, and I'm sure your parents would be able to help you if you needed it. But then what you negotiate with them is you say, we're going to monitor how much money we spend on our heating bill for the year coming up. And what you want is you want the savings. Because after all, this is your expenditure, it's your capital outlay. You bought this thing. And so why shouldn't you get the saving? And maybe suggest that to your parents. Now, some parents are probably going to say, forget it. And I just say at that point and say, well, okay, maybe not 100% of the saving, but I think I deserve 75%. Because after all, it's my thermostat that I purchased. And negotiate with them and say, listen, you deserve part of the savings that you're going to accrue as a result of having this programmable thermostat and having the furnace come on when it's needed to heat the home. Those are some of the activities. There are some of the things that you can do to save energy, and this is what I suggest to teachers and to student groups that I speak to, as to that it doesn't have to be the big items. It can be the smaller items like compact fluorescent light bulbs or thermostats and this sort of thing. The chemical process I'm not really clear on. All I know is that when the infrared radiation that's that's been in the ground from solar energy striking the Earth's surface radiates into the air, the greenhouse gases have a particular chemical makeup that they're able to absorb that infrared radiation and then distribute it every direction. They distribute it upwards, sideways, as well as back down to Earth's surface. And that distribution and sort of trapping, if you would, trapping's not the right word. What it does is delay the release of the radiation, but that delay is such that it causes a 33°C difference in the Earth's temperature than if those greenhouse gases weren't there. The actual chemistry of how the greenhouse gases absorb that infraradiation, I don't know. It would be something that you could find out.